Recently, I've gotten interested in building a Nixie clock. However, unlike most designs that use microcontrollers, I wanted to make my design using transistors. There's actually already an existing Nixie clock built from transistors, and my design has some parts that are very similar to this design, but it has one big difference. This design, which has been around for probably 10 years, all the tubes are driven directly, and they're all lit at the same time. However, with my design, I wanted the tubes to be multiplexed. In a multiplex display, instead of having all digits lit up simultaneously, only one digit is on at a given time, and the display cycles through all the digits fast enough to make it seem like they are all on at the same time. So I've made a little flowchart which shows kind of the architecture of this existing transistor Nixie clock. Basically, you have some circuit that generates a pulse every 1 second. This could be based on a quartz crystal or on mains frequency, and then that 1 second interval signal goes to a series of counters. The first counter counts seconds, the second counter counts tens of seconds, next counter counts minutes, tens of minutes, hours, and tens of hours. And all of these counters count up in binary. So then the binary digit goes to a BCD decoder, which converts that binary number into a signal corresponding to which element in the Nixie tube should be on. And then that goes to a series of transistors, which will turn on a specific segment within the Nixie tube. And so basically with this kind of design, this is the cathode drivers and the binary coded decimal decoder is replicated for every single counter. And so all Nixie tubes are on at the same time. However, with a multiplex design, it's a little bit different. So the counters are all the same. However, what I have a multiplexer which selects one of the counters, one of the 6 counters, and it outputs the binary number from that counter to the BCD decoder, which decodes it, and then that goes to the cathode drivers and energizes one of the cathodes in the Nixie tube. Now again, there are 6 Nixie tubes, and only one of them should ever be on at a given time. So there's also needs to be not only cathode drivers, but also drivers for the anode of the Nixie tube. Lastly, there needs to be a circuit that can select which counter and which Nixie tube is being driven at a given time in order to make this work correctly, which I call the sequencer. Now, multiplexing has some advantages and some disadvantages. One of the advantages is that it has lower current usage because only one tube is ever on at a given time. Instead of 6, it uses 6 times less current. However, because a tube is only on 1/6 of the time, the brightness is going to be 6 times lower. That being said, again, because a tube is only on 1/6 of the time, ideally it should have a longer lifespan. Furthermore, with this design, you need a set of cathode drivers for each tube, but with a multiplex design, you only need one set of cathode drivers and another set of anode drivers. So you need less high voltage transistors to drive the Nixie tubes. Furthermore, you only need one BCD decoder instead of 6, so you use less components for this. Now, on the other hand, you do use more components for the multiplexer as well as for the sequencer. However, overall, the number of components is roughly similar between the two designs. So why do I choose a multiplex design? And that is because it makes implementing a slot machine effect simpler. So one of the issues with Nixie tubes is that if a single digit is being displayed for a very long time, as it would be in a clock, the other digits in that tube start to degrade. And so most Nixie clocks that use microcontrollers will have a slot machine effect that exercises all of the digits. And it would look something like this, right? And this existing transistor Nixie clock does not have this slot machine effect. So this clock would have worse lifespan of the tubes because the other cathodes are going to be degraded over time. But with a multiplex design, because I can feed any counter to all 6 tubes by overriding the default behavior of the multiplexer, it makes implementing a slot machine effect a lot easier. So here's kind of the prototype that I've been building. So if I was to build the entire clock on breadboard, it would be way too big. So I've only built part of the clock. So I only have 2 Nixie tubes, and you can see that they're counting up. They're counting a little fast, just for demonstration. So this would be like your seconds, and this would be your tens of seconds. And as you can see, they're sort of flickering, and that's because this is doing multiplexing. If you were to look at this in slow motion, you would see that only 1 tube is ever on at any given time. And as a quick kind of walkthrough through the circuit, just for testing up here, I have a crystal oscillator circuit. Then over here, I was just being lazy and using some integrated circuits to divide the frequency down. Moving over here, I have the seconds counter, which is 4 bits. There's 1, 2, 3, 4 T flip-flops. And then once it gets to 10, there's a circuit to reset it back to 0. And then up here, I have the tens of seconds counter, which has 1, 2, 3 flip-flops and the same type of circuit. Now over here, I have a circuit. I have the sequencer circuit, which controls which tube is currently on and which counter is being passed through the multiplexer. Here I just have like a power supply for testing. And so these 2 counters, they go up to what I have here is I have a basic multiplexer. And then that and that forms a binary coded binary decoder. So this is most of the decoder. And then over here I have the cathode drivers, which is a bunch of these high voltage transistors. And then since I have 2 tubes, I also have a anode driver here for 1 tube, and then anode driver over here for the second tube. And so that's kind of just the basic prototype of the design. And for the full circuit, I'm probably going to just design it on circuit boards